Alright, good afternoon. So here we are for a very late session of CENG 3306 Mechanics of Materials. Okay, sorry about that. Normally I try to get the videos up a bit earlier than this, quite a bit earlier than this. But we had some technical difficulties this morning, so I actually had to reinstall Windows on this laptop, so that I wasn't able to get this thing quite up and running in time for the morning session. But got everything taken care of, and now I am ready to begin. Okay, so in the previous lesson we learned how to find shear and moment diagrams both via integration and via the method of sections. And here in this lesson I'm going to teach the final method, the method of finding shear and bending moment diagrams via inspection. So let us study this. So let us begin. We wish to do the third method. We wish to learn the third method of shear and bending moment diagrams, V&M by inspection. V&M by inspection. Okay, so let's look at this. V&M by inspection. Now that we're going to have a few general rules that are going to guide us. Just like in the previous methods, these are determined by a few general rules, and then the rest is just practice. So the general rules first is going to be the first general rule is going to be that vertical loads shift the shear diagram up or down. So if you have a vertical load, it will cause the shear diagram to jump upward. If you have a downward load, it will cause the shear diagram to jump downward. Simple enough. And so a positive load is going to an upward load is going to have the tendency to produce positive shear, and a downward load is going to have the tendency to produce negative shear. Okay, second rule. Concentrated moments cause jumps in moment diagram, and this can be a little bit confusing. But this is actually, this may be a bit counterintuitive to what you've experienced before, but counterclockwise point moments will actually cause a negative jump in moment, and clockwise moments will actually cause a positive jump in moment. And this is due to internal reaction forces. So in other words, if you apply a positive moment externally to a member, the internal moment must be negative to balance that out, or must become more negative to balance that out. Finally, if we have a free end with no concentrated force or moment, well, we're going to have a certain condition, and that is going to be M is 0 and V is 0. And also to this we could add that on pin ends, wherever we have a pin end, M must be equal to 0. So again, these are basically our boundary conditions from before. So we'll look at that. And then finally we have one more rule. Which states that, remember the integral relationship. M is equal to the integral of V dx. In other words, this is an area function. This is an area function. This is an area function. So what this means is we will find the change in the graph of shear by looking at the area under the load curve. And we'll find the change in moment based upon the area under the shear curve. And so maybe that doesn't make quite sense. Maybe that doesn't make a lot of sense yet. But let me work through an example to illustrate this. Okay, so let's work through an example here. So let us say we have a free body diagram like so. It's another simply supported beam, a nice, friendly, simply supported beam. Like so. So pin on this end, roller on this end, and I am going to have a load like this across. I am going to have a load. The only load is going to be a 20 Newton per meter line load along the top. 20 Newton per meter. And this load does not go all the way across. It is actually only active across a portion of it. And the dimensions are as follows. Alright, so let me give you the dimensions. And this is going to be 4 meters, 6 meters, and 4 meters here. Now, I could go and find the reactions and list that very clearly and list that as a separate step. So really that's the first step, but I'm going to kind of skip that because we're a little short on time today. So I'm just going to say that this is clearly 60 newtons. You can just take, this is clearly a symmetrical system. You can take the total area load, or you can take the total, you can take the newtons per meter, multiply by 6 meters, that's 120 meters, or that's 120 newtons, divide by 2. Since this is symmetric, you can only do this because it's symmetric, the load on either end simply must be 60 newtons by symmetry, and there is no force in the x direction. Okay, so really the first step is to find the loads, or find reactions. And then the second step is to get free body diagram. We already have that. Okay, so how do we find this then? How do we move on from here? Well, the next step is going to be to draw the shear diagram. Draw the shear diagram. Well, let me draw that. So I'm going to do this by inspection. What does that mean? Well, let us look at this. So I have point names A and B. This is A and this is B here. Now, the way I'm going to handle my shear diagram is like this. We remember the principle that we just mentioned, that a positive upward load is going to cause an upward jump in the shear diagram. So that means when we start here on the left, well, this can be thought of as a load. It's a reaction, but can be thought of as a point load. And so this is going to immediately cause a 60 Newton jump in the load. 60 Newton. Then, between A and the start of the line load, we're not going to have any load. So that means if there's nothing to change it, then it's simply going to be horizontal. Or if you want to think of it this way, W, if you think of W as a function of x, the W of a function of x, or W as a function of x from 0 to 4 meters is just 0. And the integral of 0 is going to be a constant. So we end up with a constant value function here. Now, let's see. You know what? I'm going to add some tracer lines. These won't be part of the actual diagram itself. I'm just trying to make approximately vertical alignment between the portions of this diagram. This would be best done on engineering paper, then you could directly make things to scale and below each other, etc., etc. Okay. Now, let us look at this. So between the start of this load, the start of the distributed load and the end of the distributed load, what do we see? Well, we have a constant value load. We have a constant value W. And I know that the change in the shear function is going to be equal to the area under the load function. And the area of this is simply a rectangle. And this then is 20 Newton meters times 6 meters. Its area is 120 newtons. So what this tells me is that between this location and this location, we are going to have a drop of 120 newtons. Our shear is going to drop by 120 newtons. Now the question, so I already know just right here that by the time we get to the end point here, we will have dropped down 120 newtons, or we will have a value of negative 60 newtons. The question then becomes, okay, what kind of curve do I draw between these 2 points? Well, I simply say, oh, this is a constant value function. The integral of that must be a linear function. So we will have a straight line going between these points. And then finally, from here, from the end of the distributed load to the end of the beam, we have no load, so we're just going to have a constant value function again. So we just drag this horizontally across, it just remains constant all the way across, and then the load at the end makes it bop back up. The 60 Newton point load at the end makes it jump back up again. So again, how I got this, the whole basis of this was, note, v of x is equal to the integral of negative w of x dx. However, from the fundamental theorem of calculus, we can see that v of b minus v of a is equal to the integral from a to b of negative w of x dx. It's that change in the moment. It's the change in the moment that's important. And so again, the total change in moment from here to here is 120 newtons. Now, let me shade these a little differently. I want to divide this into regions that I'll then find the areas of. So I think in purple, I'm going to, so that's basically the completed the completed shear diagram. I'm going to divide this into 2 regions. I know this one is going to be the same area as this one. This is a symmetric system. I'm going to call it 1 and 1. And then the middle portion in green I'm going to call 2 and 2. 2 and 2. Here. Like this. And so I'll find the area of each of these. Well, let's see. For area for portion 2, area 2 is going to be simply 1/2 base times height. This is a triangle. So 1/2 times 3 meters times 60 newtons is going to be equal to 90 Newton meters. Now, notice I did this without any kind of magnitude on it, or sorry, without any kind of positive or negative on it, no kind of sign. What I'm really saying here is that this portion from here to here is going to have an increase in moment of 90 Newton meters, and this portion from here to here is going to have a decrease of 90 Newton meters. So we'll need to consider that as we go forward. Okay. So let's see. Now let us find the I need to actually find the other, before I write the moment diagram, I need to find the area of the other piece. Area for 2, well, that's going to be, let's see, it's just a rectangle. So it's going to be 60 Newton, or actually this is area for 1, derp. Area for 1 is just 60 newtons times 4 meters is 240 Newton meters. That means from this point to this point, from the left end of the beam to the start of the distributed load, the moment diagram is going to increase by 240 Newton meters. And then from the end of the distributed load to the end of the beam, we're going to decrease by 240 Newton meters, because this one is positive and this one is negative. So then, let me draw my moment diagram. here. Now, I know, so I will need some endpoints. I need some end values. Well, thankfully there's a pin and a roller on either end, so I know the values quite well. This must be a pin, or this must be 0, and this must be 0, simply because neither a pin nor a roller can support any moment. Neither a pin nor a roller can support any moment. Okay, now let us look from here to here. Well, like I said, this is going to increase by 240 Newton meters, and this is going to be a linear equation. So maybe I'll put an L here to indicate linear, and this is actually, then you know what, let me put a line down the middle too to show where that lines up. Like so. Then from here to here, I'm going to have a parabolic behavior. This is linear, so this has to be a parabola. Like so. So I'm going to put maybe I'll put a P here showing its parabola. And I'll put the values on later. This is going to be parabolic also. And then this is going to be linear, like here. Okay. Now, if I did this right, I drew this a little funky. This slope should be equal and opposite of this slope. This one should, the curve should just kind of seamlessly blend into the linear equation. In fact, let me fix that. So something more, nope, not like that. Something more like this. Let me try to get that. That makes me happier. And this is going to be parabolic, and this will be linear. Then let me give you the values of the points, or the values of the shear points, or the moment points, sorry. This again would be 240, 240, and this is going to be 240 plus 90, which is going to be 330 here. So we started at 0, we add the area of 240 linearly from this piece. Then we add the area of this triangle, but we add it parabolically. Then we subtract that area of the parabola. Then we add this area, then we subtract the area of the triangle in a parabolic fashion. Then we subtract the area of the rectangle in a linear curve. Okay? And this whole thing, we can also note, is going to be in positive bending. This is in positive bending throughout, which is very common for simply supported beams with downward load. So this is positive bending. There you have it. That's the moment of that. That's the moment diagram there. Looks like a very happy shearing moment diagram. Oh, and let me point out again, these are 0 and 0. And then let me give you a few notes for these. Note, m of x is again equal to the integral of v of x dx, and also we'll have a downward dm of x dm dx when v of x is decreasing. Oh, sorry, that shouldn't be a 0. They should just be have a couple arrows like this. When d of m, when the v of x is decreasing, this will be downward as well. This will be negative. And then when, sorry, I should explain this. I don't like how that sounds. dm of x will be decreasing when v of x is, actually never mind, sorry, those are the same thing. The derivative of the moment is the shear. Sorry about that. In other words, where this is increasing, the shear will be decreasing as well. So where this has a negative slope, the shear is decreasing. That makes sense. And also, when v of x equals 0, what happens when v of x equals 0? Well, that means that dm dx equals 0. Therefore, this is a min or max. They go hand in hand. Wherever the shear is going to be equal to 0, because the shear is the derivative of moment, this will, the moment will have a minimum or a maximum value. All right, let's work through another one. So I'm going to work through another example, and again, this time I am going to give it, no, I'm sorry, I'm just going to provide the reactions. So example, here. Maybe I'll call this example 1 for today, and then maybe I'll have example 2. Exemple 2. Okay. Alright, so I'm going to have a cantilevered beam. You know what, I'm going to draw this a little bit bigger so that I can show things more effectively. I'm still going to try to draw everything below each other, but I am going to just draw it a little bit longer. And hopefully this will be a more clear diagram. Not that hopefully the other one wasn't too bad. But anyway, okay, so this is going to be a cantilevered beam, and I'm going to have 2 point loads on it, except one is going to be a point moment, 100 Newton meters, and then I'm at the middle, at the center, I am going to have a downward point load, 40 newtons. And then I think you've all taken statics. At this point, you know how to find the reactions, so I'm just going to give them to you. If I gave you just this on and I will give the dimensions, but I will actually, let me just do those right now. Let me put the dimensions on right now. The dimensions are 10 meters and 10 meters. Actually, you know what? I might put the I think we're gonna be tight for room here. So let me just say this is 10 meters and 10 meters. All right, and now let me give you the reactions that you would find from just doing a simple balance of moments and showing forces in the vertical direction. Well, Fx, or let me say actually Fx, Bx is 0 kips. Bx is 0 kips, and then By is 40 newtons upward, and Mb, there's also going to be a reaction moment at B. This is a fixed support. Mb is going to be 300 Newton meters clockwise. So it's actually opposite of what we get than what I have drawn here. I assume that it's initially counterclockwise, but it actually turns out to be clockwise in the end. So in other words, let me just actually illustrate this by erasing this arrow, because I want to turn this into a free body diagram, and just showing you exactly which way it's going to be going. So this is the final free body diagram that you get. Free body diagram. Okay, so below this, so I would say steps 1 and 2. Reactions, free body diagram. 3, I'm going to find my shear diagram. Now I'm going to use the same method of extending downwards some vertical lines for the purposes of just keeping everything semi-aligned as close as we can on a computer screen, or maybe at least as closely as I can on a computer screen. Maybe you can do better. I know my drawings tend to look like something a drunken monkey would make, but oh well. Okay, so let's do that. I'm going to draw a center line for our 0, and this is going to be our V. Now, let us consider this here. So, we start our shear diagram. Now, we know that in general, the only thing that will cause a change in the shear diagram is a vertical load. The default state for shear for an unloaded beam is 0. And as we come from the left here, we have no vertical load. We have absolutely no vertical load. We have a point moment, yes, and that will feed into the moment diagram, but we do not have any vertical load. So actually, all the way along here until this point load, our shear is 0. So I could sort of draw that like this. Our shear is actually just going to be 0. Then, once we get here, our shear diagram is going to fall down, bop down by 40 units. The 40 newtons, there's not 40 units, 40 newtons. The 40 newton point load is going to cause a instantaneous drop, a discontinuity in the moment diagram, bringing the value to negative 40 newtons. Negative 40 newtons. So this thing is going to be in negative shear. So remember, it's going to look something like this with the arrows like this on either side of it. That's what if you cut out a differential element of this, the right side would have an upward force on it, and the leftward side would have a downward force on it. And then I'm going to do the same kind of area calculation. Well, this one's going to be very easy. This is going to be area 1, and area 1 is simply, well, I know how to do that. That's just negative 40, negative 40, area 1, negative 40 newtons times 10 meters is going to be equal to negative 400 Newton meters. Okay. So, let's see. Now let's look at the moment. Now let us look at the moment. Here. So I'm going to draw another line for my 0 line on my moment. And then I'm going to say here, well, let's look at this. This 100 Newton meter point load is going to cause a jump in the moment. Now we need to go back here and realize that a clockwise moment will cause a positive jump in the moment diagram, and a counterclockwise will cause a negative jump. So it's actually opposite of what you'd expect. Again, this is just based on internal and external forces. So this is a clockwise moment, so I'm going to immediately increase by 100. M in Newton meters. M in Newton meters. So I'm going to start off by immediately bumping up to 100 there. Now, between 0 and 10 here, there is no area under the shear curve. So therefore, this is just going to be flat all the way across. Oh, that looks awful. That's bad even for me. I guess that'll have to do. Okay. And then, let's see, so this region is going to be in positive bending, like so, bending like that, with loads like that, clockwise on the left and counterclockwise on the right. Then, in the next 10 meters, I am going to drop by a total of 400. So 100 minus 400 is going to be negative 300. So this thing is going to drop down to negative 300 starting at 100. Again, that's because we have the area under this region is in the shear diagram is negative 400. That means this is going to drop by negative 400 units from here to here. So that's simply like this. And this is still in positive moment here. However, this region will be in negative moment here. And that's how you handle that shear in moment diagram. Fairly simple. All right, let's move along. Okay, finally, I would like to discuss the implications of something called a hinge. I would like to discuss the implications of a hinge. A hinge can be thought of as an internal moment release. Imagine, it's sort of like, imagine along a member. Let me sort of draw what you would see here. Let me draw what you would see here. So I don't know if you've encountered hinges before, but let me draw what they look like in a beam. A hinge would look something like this. You might have something like this here. It's sort of an internal pin. It's sort of an internal pin. It's sort of an internal pin. So imagine there's an internal pin here. And shear will transfer through this, but moment will not. So let's think about this. But to be a hinge, it's not like we have a triangle down here showing that this is a pin. No, this is actually just a hinge right in the middle of the beam. And you could imagine this as a door hinge, or if you actually wanted to see what this would look like in, say, steel design, the way I would make a hinge in steel design is I would realize that my cross section for, say, a W section, the web carries the shear and the flanges carry the moment. So if I had two beams and I wanted to put a moment release or a hinge in them, what I could do is I could join them with a plate right at their webs. Bolt that there, bolt that there, bolt that there, and bolt that there. And if you want to learn how to do this, how to design this, feel free to take my CNG 4412 steel and concrete design class. We'll have all sorts of fun there. Okay, anyway, so what does this do? How do we handle this? No jump in shear at hinge, so there will not be a sudden change in the shear. All the shear that comes into one end goes out the other. At hinge, no jump in moment at hinge, so the moment doesn't suddenly jump. Wait, so what does this do? It doesn't cause the shear or the moment to jump? Well, that's boring. Oh, I wrote shear twice. That's no fun. In moment at hinge. Okay, so what does happen? Well, moment equals 0. Moment equals 0 at hinge. That's going to be powerful. It's going to be very powerful. All right, so let me draw a example. Now, I am going to have to, as you may have seen in statics class, whenever we have an internal joint that is not a fixed joint, we end up having to divide the structure into two pieces. So I'm going to give you a hinge example. So let me call this example 3, hinges. Make sure we're still recording fine. Always going to be paranoid about that. And we are, so I'm happy. Okay. So hinge example, or example 3, hinges. So really this is almost getting into an area of structural analysis, which is another class I teach, and those of you who are in civil engineering, I'll be seeing you soon. And in structural engineering, structural analysis, we learn how to break structures up into pieces and analyze the forces within them, among other things. Yes, you did see that at a very simple level in statics, but we take it far, far beyond in that course. Okay, so consider this example here. I'm going to have a fixed support, and the beam is going to have an internal hinge. Then I'll keep going. The beam will continue. So this is the hinge. So this is also known as a moment release. And then I'm going to have a roller here. And then we'll continue on like so. Actually, you know what? Let me draw this out a little bit further. Here. Yeah, because I need a point in the middle there. Okay. So this is going to be an actual roller. This is just an internal hinge. Now let me label some points. This is going to be a little bit more complicated than the other examples, because it is more complicated. The end is point A. Let's see, the end of the hinge is point B. We're going to have a point C where a point load is going to be applied. And then we're going to have point D where the support is at, and where the roller is at, and E is the end of the beam. Okay? Let me give you the dimensions here. Let's see. Actually, I want to do that in green usually. The dimensions here are going to be 8 feet from A to B, 4 feet from B to C, 4 feet from C to D, and 8 feet from D to E. Then, let me show the loads on here. I am going to have a constant distributed load across here, 2 kips per foot. At C, I'm going to have a 10 kip downward load, and then I'm going to have a 12 kip foot moment 12 kip foot clockwise moment applied at E. Now, we need to think about this. If this were a single beam, a single continuous beam all the way through with no moment release, this would actually be statically indeterminate. We couldn't solve for the reactions using only statics. We would actually have to use something like, say, our deflection theories or our equations of compatibility that we've seen before. However, this moment release will actually make it possible to solve this system using statics alone. So I am going to show you how to find the reactions here. You probably learned this in statics, I hope you did, but if not, I want to just show you again. So reactions. If we ever have a hinge, we got to break the beam and analyze it as 2 different pieces. Always break at hinge. So I am then going to have this here. I'm going to have a system like this. Let me show the beam here. I'm going to draw it in 2 pieces, one piece from A to B, and the other piece from B to E. Like so. And then I'm going to show, let's see, the loads. Well, I have my 2 kip per foot load here, 2 kip per foot distributed load here, I'm going to have an AX here, I'm going to have an AY, and then I'm going to have an M at A, at the fixed support at A. Now I need to add sort of internal forces or internal reactions, and I'm going to just go ahead and assume them like this just by eyeballing it. Let's just say I have a BX here and a BY here. Now I could assume whatever I want. I could assume these are going either way. However, over here I have to be consistent. If this one goes to the right, this one goes to the left. The portions of these beams, or the portions of this beam must be, they simply must be, exerting equal and opposite forces on each other. So then I'm gonna, that's why I assume them this way. That's just how they turned out, but I kind of eyeballed it and thought that might work. But you could really, no matter what you assume, if you get a negative number, as long as you set them up as a balanced pair, BX with BX, BY with BY, you'll be fine. If you get a negative number, just reverse them around. Then I'll have the 10 kip force here, dy here, and a 12 kip per foot, or 12 kip foot moment on the end. So again, let me just circle this to make this abundantly clear. These need to be equal and opposite. Equal and opposite. Okay, so next I am going to draw free body diagrams of each piece in order to find the reactions. So I'm going to call this piece 1, perhaps, let's see, yes, here. Yeah, see, this piece alone is going to be statically determinate. Yeah, that piece alone will be statically determinate, and then once I get these reactions, this one will be statically determinate as well. So I'm going to start with this piece. So I'm still in the first step of just finding reactions. It's a multi-part step. This is still just part 2 react, or it's going to be part 1 reactions. Okay, so I am going to draw the piece on the right, and the forces on here are, well, not maybe I won't necessarily go all the way through it, but you'll get the idea. By, bx, 10 kips downward, a dy, and a 12 kip foot moment on the end. And again, I am only showing the forces that are on that portion of the beam. We are now treating it as it's basically what I'm doing here is the method of sections. I am saying that if something is to be in equilibrium, every piece of it has to be in equilibrium. If something is to be in equilibrium, the entire thing has to be in equilibrium. So if this whole beam is in equilibrium, this piece must be in equilibrium on its own. And in many cases, that will result making that as kind of, or breaking it into pieces will result in a statically indeterminate system. But in this case, because of our peculiar supports here, this will actually make it statically determinate. Okay, so let me just say that from apply equilibrium, or actually let me show you the dimensions on here. So this is going to be 4 feet, 4 feet, and 8 feet. And I will just say that after applying equilibrium, I'll just tell you what you get. I think you can handle it from here to get by, dy, and bx. Apply equilibrium equations. And you will get that dy is equal to 6.5 kips upward. By is equal to 3.5 kips upward, and bx, of course, is simply equal to 0. There's no horizontal loads on this thing. Now I'm going to continue on the next piece. The next piece will go from A to B, and I'm going to find the forces on here. First I'm going to illustrate the forces on there and then solve for them. Well, I'm probably just going to give you the solution again, but you would use this free body diagram to find these forces. So we found our dy, our by, and our bx, and now I can just apply those as loads on my my beam. So where by was upward on this piece, by is going to have to be downward on this piece by a Newton's third law. This is by. Bx is going to be equal to 0. And then, let's see, bx is 0. And then I have a distributed load across the top. Here. $2 kips per foot, And then the reactions at point A, I have AX, I have AY, and I have MA. Alright, and if you apply equilibrium equations, you will get the following. Apply equilibrium equations, and you will find that, let's see, that MA is equal to 92 kip feet counterclockwise. God, that looks awful. Counterclockwise. That, let's see, AY is equal to 19.5 kips upward, and that AX is just equal to negative BX, which is equal to 0. Okay, so now we would have all of our reactions. Now what I will then do is I'm going to combine them together, forming a single free body diagram. And this is where I'm going to do everything below each other. So let's do that. Here. This is going to be a combined free body diagram. I'm going to have my 12 kip foot moment out here, my 6.5 kip vertical reaction here. I don't like that. Okay. 6.5 kip reaction here, my 10 kip reaction here, and I'm going to have a hinge here, but that's not one of my loads. I just have my 2 kip per foot line load across here. Two kip per foot, and then I'm going to have a 92 kip foot reaction moment here, and I'm going to have a 19.5 kip reaction here. 19.5 kip reaction here. Alright, so let's see this now. Oh, and I'll go ahead and put the dimensions on here, just for the sake of completion. This is 8 feet. Oh, let me show there's a hinge here. 4 feet, 4 feet, and 8 feet, like this. Then let me show the shear. So I'm going to probably draw some vertical lines again. Let me just do that right now. I want to show some vertical lines here. So we're just going to proceed by finding the shear moment the same way we did before now. Just looking at areas under curves, etc., etc. Okay, like this. And like this. Okay. And then I'll go across. Okay, so I'm going to draw my 0 line for my shear here. And this is going to be my shear. V in kips. Now, we're just going to use the exact same method as what we did before. So, the point moment will not affect the shear diagram, But this 19.5 upward force will cause a jump in an upward jump in the shear. So we're going to start by jumping up 19.5 kips. So we start up at 19.5. Then, let's see, 19.5. Then, between A and B here, we have an area of 16, right? 8 foot times 16. So that means we're going to drop a total of 16 units, or 16 kips, between A and B. And since we start at 19.5 and we're losing 16, that means we're going to be down at 3 here. Or sorry, 3.5 here. And because this is a constant value function, it will be linear between the 2 points. I like how that, it's probably more accurate to have that down there, isn't it? Oh well, that's okay. So there's this, 3.5. Then from here to here, it's going to be a constant 3.5. Let me illustrate that's 3.5. Then this downward load is going to cause a drop in the shear diagram. It's going to cause a 10 kip drop in the shear diagram. So if we started out at 3.5 and we lose 10, we end up at negative 6.5. Negative 6.5. And then we're going to move horizontally across, because here there is no vertical load at all. So the shear will be constant from between these 2 points. Then this upward force of 6.5 kips will cause the shear diagram to jump back up to 0. We have no more vertical loads, therefore the shear diagram will simply stay 0 until the end of the beam. Here. And so we can look at these different sections. This is going to be in positive shear. So everything up to this point is going to be positive shear. This is going to be in negative shear, like so. Now let me recognize that I have 3 areas that I'm going to need to. I have 3 pieces that I'm going to define the area of. Now I know I drew this a bit low. Like ideally, how this would be is this would line up directly with this, but there's no vertical jump in the shear here. I just can't draw. Okay, so let me consider 3 areas. I'm going to have 1 here. I'm going to find the area of these 3 pieces. 1 here. And it may seem that this is a triangle. This is actually a trapezoid because this doesn't actually go all the way to 0. So therefore, this is going to be a trapezoidal area calculation for 1. So the area of 1 is simply a trapezoidal area. 1/2 of, this is the triangle portion of it, 8 times 16, plus the area of the rectangular portion, 8 times 3.5, which is then going to be equal to 92 kip feet. 92 kip feet. And the other areas are going to be even simpler. They're going to simply be rectangular loadings. So this is going to be piece 2, and the area of piece 2 is going to be 3.5 kips times a length of 4 feet. So we get a moment of 14 kip feet. Positive. And then finally, this third piece, which I will do in blue, I'm going to call piece 3. Area of the third piece, area 3, is going to be negative 6.5. Negative 6.5 kips times 4 feet is equal to negative 26 kip feet, like so. Alright, moving along. So now let's actually find the moment diagram. This will be the final step. And here the moment will be in kip feet again. Again, this will be in kip feet. Ideally, I'd put these labels on the same side, but I've kind of run out of room here. So this counterclockwise moment, if we remember, counterclockwise moments are going to cause negative drops in the moment diagram. So we're going to start at 0, and then right immediately we're going to drop down negative 92. Negative 92. Then we are going to gain a total of, in piece 1 here, we're going to gain a total of 92 units. And so the math actually works out just as we'd expect. We gain 92 kip feet, which will bring us exactly to 0. So here we're going to be at 0. The math worked out just fine. Then, as this is going to be linear, as this is linear, the integral of that, of course, is going to be a parabola. So we're going to have I'm going to draw a parabolic behavior here. That's a very poorly drawn parabola. So do notice one thing here. Our slope, if I could draw an ideal parabola here, the slope becomes shallower as the value of the shear decreases. So the slope of the moment becomes shallower as the slope of the shear decreases, or sorry, as the value of the shear decreases. It doesn't quite actually reach 0, but there you have it. The actual slope, if I were to draw this very accurately, would not come to horizontal at the point. It's because the slope would actually be the 3.5. So it's not actually equal to 0 here. Then, let's see, this piece here, we are going to have a gain of moment of 14 kip feet. So let's call that 14 between here and here. And then, because this is a positive area, it'll go here, and because this is linear, because this is a constant value function, the integral of that is a linear function. So this is going to be I'm going to erase that, looks really bad. It's a linear function. Here, so this is linear. And then, between here and here, I'm also going to have a linear function, and this is going to have the area of negative 26. So 14 minus 26 is actually going to be negative 12. And this is going to drop us down linearly to negative 12. And if we wanted to, we could use similar triangles to find the point of intersection there, or the point where the moment is 0. And then finally, because there's no vertical load, or because there's no shear between here and here, the moment diagram is just going to be flat, constant. Oh, you know what? I don't like that. More like that. And that's going to be negative 12. And finally, this clockwise moment is going to cause a positive jump in the moment diagram back up to 0. And right at the end of the beam, because it's a free end, it should be 0 there. So that makes good sense. All right, that will do it for this lecture. This is just a final lesson on finding shear in moment diagrams, and I will be posting another lesson later today. All right, thank you, and that will do it.